maximum refractive index times the length of our grid, nz times dz, divided by the speed, c naught. So our total simulation time, t, will be two offsets. Remember our source offset. We have one offset that'll take us into the middle of the source, and then another offset that'll take us out of the source. So just including two of those is pretty much just the source. We need extra time to let that source interact with devices on our grid and stuff like that. So what I like to do is add about 3 propagation times. That lets a wave bounce back and forth 3 times before the simulation ends. Now, if we're simulating a highly resonant device, we would need to account for more propagation times. And in fact, there's more sophisticated ways that we can calculate the total number of steps, but this works just fine for right now. So finally, the number of steps is the total simulation time divided by the time step. Now, chances are that will not be an integer quantity, so let's round up. And that will give us the total number of steps. Last step in the source is to actually compute the source. And first we need a time axis. We'll just use the variable t again, overwrite what we had there before. So we're going to go 0 to steps minus 1. So right now it's an array that goes 0, 1, 2, 3, 4, 5, all the way up to whatever. If we multiply it by dt, now suddenly t becomes the actual time associated with each time step, probably in femtoseconds or something like that. We'll need to know where to inject the source along our grid. So this will be the array index, and we want this to be right in the middle of the grid for now. So NZ source is the position of the source. And we're going to inject this right in the middle of our grid. Then finally, we're going to calculate our Gaussian source. And we simply just type in the equation for a Gaussian. Just to make sure this is right, let's plot it. And then we'll break so it doesn't run the rest of the code. We made an error. Something misbalanced. We need a dot to the second because t is an array. And this does a point-by-point squaring. Okay, there's our source. Let's enlarge this and talk about what's going on. So along the horizontal axis, this is the time of our simulation. We start at 0 and we go up to 1.3 times 10 to the 8 seconds. And here's our source, and it happens right at the beginning of the simulation. Had we not put in the offset, 0 would be located right here with respect to our pulse. We would have started right in the middle of the pulse, and that causes problems. We always want to ease into a source and ease out of it. So that's exactly what we're doing. We're easing into the source, and we're easing out of it. But we don't want to end our simulation right here because our source would just appear, but it takes time to travel, to be incident on a device, to bounce around, resonate, and then scatter outside of that and be recorded as transmission and reflection. So we need extra time where there is no source happening. But this is exactly what it should look like. Unit amplitude looks like a Gaussian. It's a short enough period to incorporate all the frequencies we're interested in. And we're ready to move on to the next step. So we'll delete this. We don't need to see that, the plotting commands. And the only other thing we need to do now is add one line of code inside of our main loop. So we initialize fdtd parameters the same way. Update h from e, update e from h. At this point, this is where we want to inject our source. Inject e source. And we're using a soft source, which means we're just adding a value to whatever field value happens to be at a certain point. So ey at nz source equals ey at nz source plus our Gaussian at time t. Now, if we didn't include this first term, and we just said ey at nz source equals e source t, that would be a hard source. And in fact, a wave traveling through the grid, if it comes across that point, NZ source, would not pass through it. It would reflect off of it. So this lets everything pass through and be a little bit transparent. So we're actually done this code. Let's run it and see what happens. And we see a Gaussian pulse that starts at the beginning. And notice it travels in two different directions. In one direction, the E and the H field are 180 degrees out of phase. In the other, they're in phase. We also starting to see some ringing and some other things happening. So let's talk about that. This is a pretty crude source. We're not really controlling it very well. And that's why we get a pulse that travels in two different directions. We don't want to do that, and we'll fix that later with what's called the total field scatter field source. The other thing to notice, let's run it again, is that the pulse, once it starts at the beginning, it bounces off the edges of the grid. See how it bounces? That is because we use Dirichlet boundary conditions, which assumes the fields outside the grid are zero. So if they're not zero, and we use Dirichlet boundary conditions, we force them to be zero. So it's just like we've put perfect electric conductors and perfect magnetic conductors at the edges of our grid. So of course the wave reflects off that. The other thing I want to talk about is this ringing. Let's go ahead and run it again. And notice we start off with pretty clean looking Gaussians. It's just as they propagate, this ringing becomes worse and worse and worse. So why is this? Remember that a pulse is a burst of frequencies that sort of happen all at the same time. Well, the fact that we have a numerical grid introduces dispersion. The different frequencies travel at different speeds. So what you're looking at is the spreading of the pulse. Now, in real materials, this happens also, but we've put air in here, which should not have any dispersion, but we're seeing it anyway, and it's just due to the numerics of the grid. We can make that a little bit better by using higher grid resolution. Let's go ahead and do that. Let's change our nlam parameter from 10 to 20. We'll never eliminate that dispersion, but we will make it a whole lot better. And notice before we would have seen more ringing. And we're just barely starting to see some now. But if we let this run, we would eventually see more. So it got a lot better. We'll set this back to 10. Another thing I'd like to play around with is this time step. We know that there's this Courant stability condition behind that. So what if we violated that? What if we made dt 10 times larger? So our time steps are too large. Let's see what happens. And first of all, we see a very crazy looking pulse, but also notice the values. This is 3 times 10 to the 251 power. Clearly this has gone unstable and exploded, which is why we have to be very careful when we calculate our time steps. Well, that's really it for this code. There's not much more we can do with this. Thank you.